The incredible J58 was a variable cycle engine that functioned as a turbojet but with an air bleed to assist a stator-reactor or ramjet. What is this? And what makes it special? In this video, I'm going to show you and simply explain how it works, but I recommend that you first see how a turbojet or turbojet works. Welcome to a new video. One of the previous videos link is in the description below. I'm Marcos and this is World of Aviation. It was the first engine capable of operating in afterburner for long periods of time and the first to be certified for AMAC 3 flights by the United States Air Force. An important feature in the J58 is the variable geometry conical intake. And of course, what we mentioned before, which is a hybrid between a turbojet and a ramjet. Turbojets are inefficient at high speeds and ramjets can't operate at low speeds, so this type of engine takes the best of both parts. Let's see how. In the wing pods of the Strategic Reconnaissance 71 is located the J58 engine, the air intake, the gas ejector, autovera, apart from the body of the plane. At speeds less than Mach 2, the J58 acts like any other turbojet. The air is directed to the gondola or nacelle and flows through the air intake. The air is compressed before entering the combustion chamber, where it is mixed with fuel and ignited, creating combustion. The hot, high-pressure exhaust gases provide the thrust and also spin the turbine. These gases exit through the nozzle. The turbine spins the compressor, maintaining the engine cycle. Right after the turbine, there's the afterburner device, where more fuel is added to the gas exhaust to get even more pressure and thus more thrust. While afterburners allow for a more powerful thrust, they are highly inefficient and a lot of fuel has to be used for an extra percentage of force. Here's the secret that sets the J58 apart from other turbojets. These are these 6 strange tubes that are called bypass ducts. These ducts open when the plane is flying at more than Mach 2.2, moving the compressed air from the 4th stage of the compressor directly to the afterburner. And this makes the engine act like a ramjet or stator reactor, which allows the Strategic Reconnaissance 71 to operate with much greater fuel efficiency. But what is a ramjet? Simply explained, it's a type of jet engine that lacks a turbine and compressor, that is, moving parts. It doesn't have them. The compression is carried out due to the high speed at which this engine has to fly. Here, the necessary compression already exists to ignite the fuel and carry out the combustion. Returning to the Strategic Reconnaissance 71, the combined action of the turbojet with the ramjet makes the J58 a unique engine, and we can call it a turbo-ramjet, and this allows the plane to fly at speeds that would melt a normal turbojet. Due to the speed of the aircraft, the air is previously compressed in a ratio of 38.8 to 1. And when it goes through the compressor, a proportion of 1.6 to 1 is added. What do I represent the supersonic shock waves before they reach the compressor? Do you remember the shock waves in a supersonic flight? We had seen this in previous videos. If you didn't see it, I leave you here the images of what we had discussed in that video. Here we had a plane flying at supersonic speeds and the shock waves form in the shape of a cone. Just like this bullet flying at supersonic speeds, it also forms those shock waves. The same thing also happens in the Strategic Reconnaissance 71 and in the engine nacelle. Waves are formed within this, and it's going to be very important in explaining the operation of the J58. The SR-71 as shape is as crucial for the J58 engine to function properly as the engine itself. So let's see how it works. At the entrance of the nacelle is this tip called the inlet cone, and behind this is the diffuser, where the compressed air expands into the engine. This is called the pressure recovery process. At supersonic speeds, the cone takes the first supersonic shockwave so that the engine gets the best possible airflow. Inside the air intake, a second shock wave is formed called normal, where the incoming air lowers its pressure and increases its speed. And it begins to make transitions from low pressure to high and low pressure, again in supersonic speeds to subsonic and back to supersonic. Increasing the speed, the normal shock wave ends inside the intake, and the faster it goes, the further back it will be. When the plane reaches Mach 1.6, the normal shock wave ends in the best position to recover pressure. The dynamic pressure caused by supersonic flight at this speed is used within the diffuser, and when the Strategic Reconnaissance 71 is flying at Mach 3.2, this pressure ratio is very high, up to 90%. So, to keep the normal shock wave within the optimal position for pressure recovery, the cone retracts 1.6 inches, about 4 centimeters, and this for each increase in the Mach number after Mach 1.6. This changes the inlet geometry to keep the normal shock wave in the most efficient position. And here comes the interesting part. When the plane reaches the cruising speed of Mach 3.2, the external shock wave is placed directly on the lips of the air intake, called the hood and the inlet spike. It was withdrawn, measuring 26 inches or about 66 centimeters. And this is the speed at which the J58 reaches its maximum fuel efficiency, with the pressure recovery at the inlet doing most of the air compression work to be used later for afterburning. Now that we've seen how the shape of the plane and the J58 work together, let's look at other details inside the engine nacelle. Positioned within the inlet is the bleed air part, which captures some of this incoming air and passes it through an outer ring called a shock trap, which reduces the airspeed to subsonic and guides it through the entire engine, surrounding it to cool it, and then it is expelled from the nacelle through the exhaust. At less than Mach 0.5, not enough air enters to cool the engine, so more air is made to enter through suction inlets, secondary ones that are in an intermediate position along the gondola and close after passing Mach 0.5, which occurs after takeoff and before landing. Before the ejector or exhaust nozzle, tertiary doors are installed, which also open at low speed. They prevent these from causing resistance caused by the lack of air and the flowing gases. They activate below Mach 1.2, and they remain closed for most of the Blackbird's flight, opening only for takeoff and landing, as well as during in-flight refueling. Both the intake door and the tertiary ones allow the powerful J58 to operate at much slower speeds than its speed cruise. The last details we are going to see are necessary to keep the normal shockwave in the correct entry place. The first is the cone air bleed, which connects back into the gondola at these outer gates. At low speeds, it allows the engine to draw additional air, while at high speeds, the air bleed removes the boundary layer. A turbulent, low-pressure layer of air that normally adheres to the surface of the cone and reduces pressure recovery. Inside the air intake, there are also slots that extend between the shock trap directly outside the aircraft, called front bypass doors, and through an analog computer, the pressure inside the diffuser is lowered, sending it outside the aircraft. But if the pilot wants to reduce resistance through acceleration or provide additional cooling to the engine, a bypass can be opened that directs the additional pressure through the gondola. Gondola. Thank you for watching. Until next time. My name is Marcos and this is World of Aviation.